All right, so let's get into our next lecture. So today we are going to be continuing our work in chapter 4, which is about number theory and the basic properties of the integers. So last time we discussed modular arithmetic. So this was essentially setting up, using our divisibility rules and the division algorithm, we're setting up a arithmetic, a way of adding and multiplying inside a set of finite integers. And basically this is a good way of thinking about the integers and which ones divide other integers and what remainders are. So this is like a way to start studying the integers. Today what we're going to be doing is we're going to be studying the primes and the Euclidean algorithm. So it's going to kind of continue our study of divisibility and continuing our study of the integers. Okay, so this is section 4.3. 4.2 is being skipped entirely. Okay, so last time we studied divisibility. So we introduced kind of what it means for one integer to divide another. You know, a divides b if b can be written as a times some other integer c. And we also introduced modular arithmetic. So we talked about essentially division with remainder and how to work with remainders. So we also remembered that in general, for integers a and d, we can write a is equal to d times q plus r, with r being greater than or equal to 0 and less than d, right? So this is a way of expressing the fact that in the integers, we can't always divide on the nose, but we can keep track of the remainders and do good math with the remainders, essentially. So now what we're going to be doing is we're going to be starting to explore the primes. So in a certain sense, the primes are the numbers which are not divisible by anything else. So they're kind of these foundational building blocks when you're trying to build all the integers as integers being divisible by some other number. So definition. An integer p greater than 1 is a prime if the only positive factors, or the only numbers, the positive integers that divide p, are 1 and p. Positive factors or divisors of p are 1 and p, right? For every positive integer greater than 1, it is always going to be divisible by at least 2 things. It's always going to be divisible by 1. It's always going to be divisible by itself, right? 17 divides 17, 22 divides 22, 1 divides 22. Any positive integer you pick, it'll satisfy those properties. The primes are the ones where those are the only possible numbers, positive integers, that divide the integer that you're interested in. In other words, if p is prime and a divides p, then either a is equal to p or a is equal to 1. Those are the only 2 options available to you for a positive integer. Okay. So as a remark that I want to make, we do not consider the number 1 to be prime. So 1 is not prime. And there are many good reasons for this, one of which we'll come to in just a little bit when we come to the fundamental theorem of arithmetic. Okay, so there are some examples that we can just do once we start picking out integers. So for instance, if we look at a list of 7 and 17 and what else do I have? 27 and 51. Any collection of integers, one can ask, is this particular integer prime or not prime? 7 we know is prime. It's not divisible by anything besides 1 and 7. The same holds for 17, but 27, of course, is composite. I should make a definition or a notation. If n is not prime, then n is composite. Composite number. So in this example that we have, 27 is composite because it has plenty of factors which are not 1 and 27, namely 3 and 9. And it's the same thing with 51. 51 is also composite because, for instance, it's divisible by 3. And several other numbers. These two are composite. And these two are prime. Okay. So now that I've introduced primes, it's probably pertinent for me to express why are they so useful, or why are they considered fundamental. So the reason that primes are considered fundamental is because we can always write any integer multiplicatively as a product of primes. So in this sense, the primes are the basic building blocks of the integers. Here's a theorem. Every integer greater than 1 can be expressed uniquely as a product, as a prime, or as a product of 2 or more primes. Right? So what this is saying is that whenever we consider an integer and we want to be thinking about divisibility properties in the integers, one of the first things that we can always remember is that we can always express any integer uniquely as some product of these kind of basic building blocks, just the primes. So with these examples that we had above, their prime decompositions are, well, 7 is already prime, so its prime decomposition is just 7. 7 is equal to 7. And it's the same thing for 17. 17 is prime, so I just have 17. Its prime decomposition is just 17. But 27, on the other hand, looks quite different. 27 is divisible by 3. And then if I want to, so I already know that I have a factor of 3 in the prime decomposition of 27. And then since 27 is 3 times 9, I just need to think about what the prime factorization of 9 is. 9 is just 3 times 3. So 27 is equal to 3 cubed. So here I'm just listing the prime that appeared. What I'm listing here is the way to write out 27 multiplicatively such that I'm only multiplying primes together. I multiply the prime 3 by itself 3 times and I get 27. What do we get for 51? Well, 51, I know that it's divisible by 3, right? It's going to be 3 times 17, right? 60 is equal to 20 times 3. So if I subtract off 3, I should get 3 times 17. Let me see if I did this math right. Yes, I did. Right? So the prime decomposition of 51 is just 3 times 17. I can't break 17 down any further because I already know that it's a prime. Okay. I don't expect that this is particularly new, but this is how we start thinking about primes. Okay. What else do I want to do? Oh, I can do some bigger examples, I suppose, of prime factorization. And the idea always is to try to find some factor and then break up your number further. So for instance, if I'm trying to find the prime factorization of 1,105, well, since it ends in a 5, I know that it's divisible by 5, so my first step should be write 1,105 as 5 times something. And indeed, this is going to be equal to 5. And then if I divide by 5, I'm going to get 221. And 221, okay? And now I want to ask, how is 221, what is the prime factorization of 221? And it turns out that 221 is divisible by 13 and 17. And 13 and 17 are both also primes. So the prime decomposition of 1,105 is 5 times 13 times 17. Okay, so assuming that we want to write integers in terms of primes, the next question is, how do we determine whether a particular number is prime or not? For instance, with 221, this is a big enough number that it's not immediately obvious whether anything divides it at all. And it may seem as though I pulled out 13 and 17 from a hat. So the first thing to think is, if we're trying to check if a number is prime, the most basic and naive thing to do is check every single number less than n and see if all these numbers less than n divide the number in question. So for instance, to check, say, whether 52 is prime, it is enough to check whether 2 divides 52. It does, so immediately we know 52 is not prime. Maybe I should pick a different one. Let's do 53. In order to check whether or not 53 is prime, we could check whether 2 divides 53, does 3 divide 53, does 4 divide 53, does 5 divide 53, and so on and so forth, all the way up to checking, does 52 divide 53? And the point is, this is an extremely inefficient way of going about checking whether 53 is divisible or not, whether it's prime or not. Indeed, we can see that it already takes something like 51 steps, even for a relatively small number like 53. So this is a correct way of checking whether a number is prime or not, but it's also very naive and very inefficient. So it turns out right away, we can cut down on the number of cases that we need to check to examine whether or not a number is prime. So let me write up the following. Theorem. If n is composite, then it has a prime factor that means that there's some prime number which divides n, p, which is less than or equal to the square root of n. So here, the thing that I said naively one should check is one should check all of the numbers between 2 and n. Here I'm saying, actually, you only need to check the primes in between 2 and the square root of n. Already this is many, many, many fewer cases. I can kind of show an example of this soon. Okay, but first, let's have the proof. So first we're going to, it's going to go as follows. Since n is composite, that means that I can factor it, or I can write it as a non-trivial product of two numbers. I can write n as being equal to a times b, where a and b are not equal to 1 or n, right? If they were 1 or n, then I haven't really factored anything. I've just, I haven't done anything. But if I have a non-trivial factorization, that is, n is composite, then I have some integers a and b not equal to 1 or n, such that I can write n in this fashion. Okay, my claim is that either a or b is less than or equal to square root of n. So inside this proof, I'm going to have a very small little proof by contradiction. So the claim is either a or b is less than or equal to n, for if this was not the case, so I'm negating the statement that either a or b is less than or equal to square root of n. To negate an or statement, I need to negate each thing and have an and statement. So the negation of this is a is greater than square root of n, and b is greater than square root of n. If this were not the case, then a is greater than square root of n, and b is greater than square root of n. So a times b is greater than square root of n times square root of n, which is equal to n. So if both a and b are greater than square root of n, then a times b is not equal to n. But we already assumed that n is equal to a times b, so this is a contradiction. So what I have shown with this little claim is either a or b is less than or equal to n. Without loss of generality, let me say that a is less than or equal to n. Without loss of generality, a is less than or equal to square root of n. Now, there are two cases. Case 1, a is prime. If a is prime and a is less than or equal to square root of n, then we're done. I found a prime factor less than or equal to square root of n. Case 2, a is composite. So I'll write a is equal to, I don't know, k1, k2, or let me write a is equal to p times a prime. So if a is composite, that means there's some non-trivial prime which divides a by our divisibility theorem, or the fundamental theorem of arithmetic, that every number can be uniquely factored into primes. And p is less than or equal to square root of n. because P is smaller than A, and A is less than or equal to the square root of n. So either way, I get some prime factor, which is less than or equal to square root of n. So that proves this theorem, that if n is composite, then it has a prime factor, P, which is less than or equal to square root of n. So this makes our checking much easier. So, for instance, if I want to check that 101 is prime, all I need to do is check whether 101 is divisible by the primes that are less than 11, right? Square root of 101 is a tiny bit greater than 10. So I actually really only need to check, primes less than 11. So check, does 2 divide 101? No. Does 3 divide 101? No, 3 divides 99, and then, so 3 divides 102, not 101. So no. Does 5 divide 101? No, this isn't a multiple of 5. You can tell by the last 2 digits. Does 7 divide 101? Well, we can just kind of check it out. So 7 divides 77. So 7 divides 84. So 7 divides 91. So 7 divides 98. So then 7 divides 105, but we've skipped right over 101. So no. So in particular, 2 does not divide 101, 3 does not divide 101, 5 does not divide 101, 7 does not divide 101. And these are all the primes that are less than 11. 2, 3, 5. Yes, I am correct. So just by checking these 4 cases, I can already tell you that 101 is prime. And this can be used to great effect even to check that, for instance, 53 is prime. Now I only need to check primes less than 8. So I look at the exact same list. Does 2 divide 53? No. Does 3 divide 53? No. Does 5 divide 53? No. Does 7 divide 53? No. So I'm already done. I know that 53 is prime as well. Great. So we have a slightly faster way of checking whether a number is composite or whether a number is prime. Okay. So what we're going to do next is maybe the high point of this whole section, this whole chapter perhaps. This is a absolutely beautiful proof. Before I get to this proof, let me mention a couple of facts. First of all, I haven't proven the fundamental theorem of arithmetic for you. I haven't proven that every integer can be written uniquely as a prime or as a product of 2 or more primes. Right? I just wrote it down, but I didn't write a proof. The proof requires material from chapter 5, really. It requires induction. So we will get to the proof of the fundamental theorem of arithmetic later. And that theorem is certainly necessary for this upcoming proof. So there is a gap in terms of what I have proven for you, but we will fill this gap when we get to chapter 5, essentially. The other thing that I want to note is one valid reason for not considering 1 as a prime is because if 1 were a prime, then we would not have a unique way of writing numbers in terms of primes, right? If 1 were prime, we would not have unique factorization. And what I mean by that is very simple to see. For instance, 12 can be uniquely written in terms of primes as being equal to 2 squared, which is 4, times 3. So the things that I need to keep track of are that the 2 comes with the power of 2 and the 3 comes with the power of 1. If 1 were a prime, then 12 could also be written as 2 squared times 3 to the 1 times 1 squared, right? 1 squared is just 1, so this is the same. 12 would also be equal to 2 squared times 3 to the 1 times 1 to the 507, right? So if 1 is a prime, then it completely wrecks our notion of being able to uniquely factor a number into primes. There are further reasons why 1 should not be considered a prime, but here at least is 1. We want unique factorization of all integers into prime numbers. Okay. So the next step that I want to do is I want to show that there are infinitely many primes. So the claim is, so theorem, there are infinitely many primes. This is another very, very beautiful proof, and it will proceed by contradiction. So proof by contradiction. So to contradict the statement that there are infinitely many primes would be to say there are only finitely many primes. And if there are only finitely many primes, then we can list them all, P1 through Pn. Assume that there are finitely many primes and we list them all, P1 through Pn. Now we're going to construct a new number. Define or set Q. I'm making some number. Q is going to be the number equal to the product of all of these primes, P1 times P2 times P3, all the way up to times Pn, plus 1. So I have some finite number of primes. I make a new number by multiplying all those primes together and then adding 1. Okay. So claim Q is either prime or composite. This is true, right? We started off by defining what prime numbers were, and we said that all integers which are not prime are composites. So the claim is that Q is either prime or composite. Okay, let's break this into cases. Case 1, Q is prime. Then what this does is this contradicts the facts that we have listed all primes P1 through Pn, because Q is certainly bigger than any of the Pi, right? It's bigger than any of the primes that are listed here. Then Q is not on the list. And then we get a contradiction. So in case Q is prime, we have already contradicted that we listed all the primes here. Now, it's not necessarily the case that Q needs to be prime. The second case, case 2, says Q is composite. Well, if Q is composite, that means there must exist some prime P which divides Q. So P divides Q for some prime P. Okay? So if Q is composite, it's divisible by some prime P. I claim that this prime P, which divides Q, cannot possibly be one of our lists. Note that P is not inside the set P1 through Pn. If P is equal to Pi, that means if P is already on our list, then P divides Q, but P also divides this product of primes, P1 times all the way up to Pn, right? Because it is one of the factors. If P is equal to P10, then by assumption, P divides Q, but P also divides P1 times P3 times whatever times P10 times all the way up to Pn, because it literally appears in the multiplication. But if P divides Q and P divides this thing, then P divides Q minus P1 times all the way up to Pn. This is from our last lecture. If P divides two numbers, then it'll divide the difference of those two numbers. But this implies that P divides 1, because Q minus P1 through Pn is just 1. So that implies that P divides 1. But no prime divides 1, right? In the integers, nothing divides 1 except 1 and -1, and those are not primes. So P cannot be on the list. Which is a contradiction, because we assumed that we listed all of the primes here. Contradiction. And this finishes the proof, right? We assumed that there are finitely many primes. We got 2 cases, and then in each of these cases, we showed that we arrived at a contradiction. So there's an important thing to notice here, and this is kind of a frequent flaw, is that it is not the case that I am saying that Q is prime. That is not what I'm saying. I'm saying we produce a number Q, and then there are 2 options. Either Q is prime, or Q is composite. If Q is prime, then Q is not on the list, and we're done. If Q is composite, there must exist a prime which divides Q, and then I show that that prime also can't be on our list. So the new prime that's not on the list is either Q or this prime P which divides Q. This is a wonderful, beautiful proof, and it's been known for thousands of years. And it is inconceivable that we do a proofs class or a 381 class without at least seeing this proof. But once again, notice that I heavily use the fundamental theorem of arithmetic, which says every integer can be written uniquely as a product of primes. So remember that the thing underlying this beautiful proof is that every integer can be written as a unique product of primes, and we haven't proven that yet, we're just using it. Okay, how are we doing on time? We have 2 minutes left, so why don't I stop here?